Right, so we just showed that two resistors in parallel can have a single equation that gives the combined resistance, or R total. Apologies for this, by the way, but it's my most advanced tripod with my visualizer camera on it, which is just another webcam cable tied onto my camera tripod. So it is getting in the way a little bit, but I'm trying to keep the paper upright. Okay, so we saw for 2, well now let's do it for n. Now n, mathematicians rather, like n because it just means any number. So let's go to where we were before. We're assuming DC. We've got resistor R1 here. We've got resistor R2 here. We've got resistor R3 here. R1, R2, R3. Now, as in maths, it means you can't be bothered to draw the rest, and I'm going to draw this as a dotty one as well here. Not a very good drawn resistor, it's a bit fat on one side. So R to the N. So what we're asking here is we want a formula that gives us the total resistance, R total, for all of those resistors in parallel. A bit daunting when you first look at it, but it's not really, because what we have here is, this is the total current flowing through the whole circuit. Must be, because it's the only feed point into here. And as before with the 2 resistor case, what we can do is we can say, well, this is little I1, this one's here is little I2, dot over the top. This one here is little I3, and this one here, no surprise, is little I-N. Okay, we're getting somewhere now. So we can also say that this big I here, the total current, is just equal to the sum of the little currents. Again, the mathematical dots that mathematicians like, meaning we can't be bothered to write the rest that are in here, and we end up with that. Okay, well, as before we can say that the voltage here is common to all of these, so we can say that little I1 is actually just V upon R1, V over R equals I, right? So, according to Ohm's law, so we can say that that's equivalent to V upon I1. R1. V upon R1, we can say that I2 is equivalent to V upon R2, you get the idea, V upon R3, and finally we have V upon Rn. So that's starting to look like something that we might be able to do something with. If I take the V across to the other side, so what I can do is I can just, well, I can do this. So I can say that I is equal to, take the V out, and I end up with 1 upon R1 plus upon R2 plus 1 upon R3 dot 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 1 upon R to the N. So all multiplied by V. The advantage of taking that out is now I can move it to the other side, and what I end up with is I upon V, note I upon V, is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 going to 1 upon R to the N. But I upon V isn't anything very useful, because I upon V is not the resistance, it's the admittance. So we know for a fact that R total the total resistance must be equal to V divided by I. So in other words, the combined resistance of all these up here must just simply be V divided by I. So R total equals V upon I. Yeah. So if I shift that about, what I end up with is I upon V is actually equal to 1 upon R total. So what that means, take that, take that, what that means is I end up with this final equation, 1 upon R total is equal to 1 upon R1 plus 1 upon R2 plus 1, sorry, move it up a bit, upon R3 dot 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 1 upon R2n. Okay, how neat is that? So now we have an equation which relates any number of resistors in parallel and enables us to calculate the equivalent resistance of all of those resistors in parallel. Who said electronics isn't magic? And it gets more magic because we're just playing with DC at the moment. Wait until we start playing with AC. Okay. Good to go, I think. Hi, welcome back. Now here I want to ask a couple of fairly fundamental questions, and really that's what is a capacitor and what is an inductor. So if we look on the sheet here, so the symbol for a capacitor, broadly speaking, is that. Now, as with all symbols, they have some indication of actually what that device looks like inside, if you like. And I think most of you are aware that capacitor is just two plates that are quite close to each other, but not quite touching one another. So in other words, what we have here is we have a plate here and a plate here, and if I were to draw them like this, maybe that becomes a bit more obvious. With a connection here and a connection here, and what we have is a gap in between here. Now that gap in between those two plates ultimately determines what the capacitance of that device is. But also, now having knowledge of what the capacitor physical makeup is, that gap isn't necessarily air. It can be, but often there's an electrolyte in there, which can either be a liquid or a solid or a crystal or something like that. But that gap in there, that physical gap, means something rather obvious to us, I hope, in that if we connected this onto a DC source, so it would seem fairly obvious, I think, that you're not really going to get a current flow going through here if we just put a load on here. We need a load for everything, and a load can just be a resistor. If we put a load on here and we connect a DC source to there, we're not going to expect much current to flow through the load, are we? Because this is open circuit. It's effectively, what we've done is we've taken a closed circuit. Imagine this capacitor isn't here and there's just a straight wire going across here. It's a bit like we've just cut the wire, and it should come as no surprise that by cutting that wire and making that open circuit for DC, now think what DC is. Direct current. What's the frequency of DC? Well, frequency is measured in hertz. So this doesn't change with time. This is always positive, this is always negative. So the frequency is equal to 0. for DC. Now at DC, no current will flow in that circuit. Okay, that's capacitors at DC. What about an inductor? So, an inductor, many of you I hope will know, not excuse me, not amazingly well drawn, but that's a coil of wire. Just move the camera this time, see if that's a better way of doing it. Yeah, I think it is actually. So you've got an inductor, which is effectively a piece of wire wrapped around a pencil or around a former or something like that. So we can do the same thing. We can connect plus, minus, like this. We can make a circuit. Let's put a resistor in there as a load. And B here. Now what do you think is going to happen there for the DC conditions? So at DC, I don't know, as I said before, people feel more comfortable with numbers, so say this is 5 volts, it's immaterial, it could be 1 volt, 100 volts. So say we've got 5 volts here. What would you expect to happen under this situation where you put an inductor in the way? Well, forget the switch on conditions or anything like this, we're talking about steady state. So what we would expect to happen is, well, this is just essentially a piece of wire. It's going to have some resistance, but probably not very much if it's only a few turns. So what's going to happen is current is going to flow through here at DC. So at frequency equals 0, this is going to appear as a short circuit, and this one here, the capacitor, is going to appear as an open circuit. Okay. Not very exciting at the moment because we want to be able to do a bit more than just block something or let it through. Actually what we want to be able to do is we want to be able to selectively block things or selectively let them through. So DC's fine, so if we had to block, we would know we could just put a capacitor in the way, but that's not much better than cutting the wire. And if we wanted to let current flow in the circuit, we could put an inductor in the way, but that's not much different to putting a wire there. So at the moment we don't have any real plausible reason to want to use capacitors or inductors, but that's just really a very, very brief overview of what we're up against here. Okay, we'll move on to the AC case in just a second.